how many of you have ever been in a planetarium before? A whole bunch of you. That's wonderful. How many of you have been in this planetarium, the Morrison? Fantastic, welcome back. From those lucky few, does anyone here remember the old Morrison? The classic model? Quite a few of you. That is great to see. Now, for those of you who never got a chance to see it, it was a really special place. We had a slightly smaller dome, only 65 feet across instead of 75. It was untilted and had a big cutout of the San Francisco skyline all the way around the edge. That was cool. But the room was dominated by that huge thing in the middle. We called it the Academy Projector. It was massive. It looked like it was made out of parts from a Navy destroyer. You know why? It was made out of parts from a Navy destroyer. It did project a beautiful night sky, though, as seen from any place on planet Earth with a San Franciscan skyline, so pretty much just San Francisco. But using that projector, we made shows here at the Academy, something we are proud to continue in our new facility. So the show you're about to see is our most recent production, called Incoming. Now, we are talking about the hard-hitting stories that make a planet Earth, and to tell a story like this, you need an amazing narrator. So we got George Takei. He does a wonderful job, but as you're listening to the dulcet sounds of his voice, you might notice about halfway through, there's a distinct change. And that's because my George Takei impression is awful. I'll be speaking during that part, sharing with you a little bit of insight, a little bit of change that happens so quickly in astronomy. New discoveries are made all the time, so it's my pleasure to share some of that new information with you. So quick check. How many of you folks have heard of Planet 9 before today? Quite a few of you. We're hopefully going to give you a little bit more information by the time you depart. But for right now, a few important favors to ask. Number one, we hope you came in to find nice, clean seats. In the interest of keeping them that way, we do ask, please, no food or drink in the Morrison. Number two, we also have these super cool, super bright digital devices on our person, in our pockets. They do amazing things, but they also make lots of light and sound. If you have not already, please take a moment now to turn them off, deactivate them, set them to stun, do whatever you have to do. Just make sure they do not pop out during the show. We'd also like to ask you to remain seated for the duration until the lights come up at the very end. This is most importantly for your own safety. Our stairs are very steep. They're made of concrete, and it really hurts when you trip and fall down them in the dark. Trust me, I know. We'd also like to ask you to remain seated because we use projectors to make the images you're about to see. If you made your way up the stairs during the show, you would pass in front of at least one of them and make a giant person-shaped hole in the universe. This is not scientifically accurate. Please refrain from doing so. So with that, I invite you all to sit back, relax, look into the dome before you, and enjoy our show. Incoming.
Earth teems with life. Even here in the Arizona desert, shady nooks conceal diverse plants, and many species thrive in this hot, dry environment. Life is shaped by influences from beyond Earth, by the light and heat of the sun, of course, but also by rare, sometimes catastrophic events. Our journey begins with one such event in the story of life. We're looking at a magnificent scar on Earth's surface, a crater that formed almost 50,000 years ago when a visitor from space collided with our planet. That visitor was an asteroid that vaporized on impact. It explosively, instantaneously formed what we now call Barringer Crater. Asteroids and comets have collided with our planet throughout its history. They have changed the course of life on Earth, and they may have brought the ingredients of life to our planet billions of years ago. An asteroid about 30 meters across created this kilometer-wide crater. When that metallic space traveler struck Earth, it devastated the local environment. Geological activity erases almost all evidence of these impacts, but we have identified nearly 200 impact craters dotting Earth's crust. We study the geology around these craters to determine when the impacts occurred. They range in age from thousands to millions to billions of years old. The age of one crater implicates it in a global calamity that took place 66 million years ago. We can't see it as clearly as the crater where we started our journey, but tiny variations in Earth's gravity around Mexico's Yucatan Peninsula reveal underground concentric rings, the largest nearly 200 kilometers across. Chicxulub crater. An asteroid about 10 kilometers in diameter caused this damage. The impact ejected debris that fell to Earth for hours, with hot rocks raining down around the globe. The initial burst of energy and the firestorm of secondary impacts superheated Earth's atmosphere. Soot darkened the skies for months, interrupting photosynthesis and cutting off the food supply for innumerable species, including most dinosaurs. We find geological evidence of this event all around Earth in a global layer of dark clay that bears an extraterrestrial chemical imprint. A city-sized visitor from space 66 million years ago changed the story of life. To learn more about these visitors to Earth, we have sent spacecraft to explore asteroids and comets. Let's follow them to this final frontier. Astronauts have only traveled as far as our nearest neighbor in space, the Moon. But our robot explorers have voyaged throughout the solar system. We learned the planets' names early in life: Mercury, Venus, Earth, and Mars, along with the giants, Jupiter, Saturn, Uranus, and Neptune. But we have many other fellow travelers around the sun, including rocky asteroids and icy comets. Left over from the formation of the planets, these little guys hold secrets to the origin of our solar system. Cool comets reside far from the sun, but most asteroids orbit between Mars and Jupiter. Let's visit Vesta, an asteroid responsible for many impacts on our planet. We can think of Vesta as a building block that could have combined with others to form a planet, a lingering remnant of our solar system's formation. NASA's Dawn spacecraft orbited the 500-kilometer-wide asteroid for more than a year. Dawn discovered that water may have flowed briefly on Vesta's surface, which fits with the idea that asteroids or comets may have brought water to Earth billions of years ago. Vesta's devastated South Pole shows evidence of a major collision that took place about 1 billion years ago. It excavated quadrillions of tons of rock and debris. fragments from that collision have made their way to Earth. About 1 in 20 of all meteors that fall to Earth originally came from this one asteroid. Vesta is one of the largest asteroids. Only a few hundred asteroids have diameters greater than 100 kilometers. City-sized asteroids are far more common. If we look for asteroids 10 kilometers in diameter or larger, we expect to find about 10,000 in the asteroid belt. Medium-sized asteroids with diameters greater than a kilometer number nearly 1 million. And perhaps hundreds of billions of asteroids are smaller yet. Let's visit one of these smaller ones. Little Itokawa travels closer to the Sun than most asteroids. It's just over half a kilometer long, about 6 football fields. A rubble pile held together by weak gravity. Itokawa was likely born in violence, the product of an ancient collision. Itokawa began its life farther from the Sun. So why did its orbit change? Although tethered to the Sun by gravity, asteroids also experience smaller gravitational tugs from the giant planet Jupiter. And they respond to the Sun's warmth by changing their rotation and speed. These influences cause asteroids' orbits to change slightly, sometimes sending them hurtling toward the inner solar system and Earth. We know of tens of thousands of these objects. We call them near-Earth objects, or NEOs, even though most of them don't get anywhere near our planet. Itokawa and other NEOs formed in the main asteroid belt between Mars and Jupiter, but they got nudged closer to the Sun over many, many orbits. Some comets have migrated in from even greater distances. Mere decades ago, an encounter with Jupiter diverted Comet 67P, Churyumov-Gerasimenko, nicknamed Chury, into an orbit closer to the Sun. This made Chury an accessible target for the Rosetta spacecraft. In November 2014, Rosetta released a washing machine-sized lander called Philae to touch down on the comet. After a bumpy landing, Philae detected the precursors of molecules important for life. From orbit, Rosetta also found that water molecules evaporating from the comet differ slightly from those we find on Earth. They don't match. If our planet's water came from space billions of years ago, it may have arrived on comets, but not comets like Chury. Comets originate far from the Sun in the deep freeze of our solar system. Chury probably came from beyond the orbit of Neptune, the most distant planet. We have discovered more than 1,000 such icy worlds. The most famous of these? The ever-popular dwarf planet Pluto. When we look at Pluto's orbit, we see something wildly different from the planets in our solar system. Its orbit appears stretched and tilted. And Pluto revolves around the Sun twice for every 3 times Neptune does. This perfect ratio kept it from getting kicked out of the solar system altogether. Other objects were not so lucky. More on that in a moment. First, let's take a closer look at Pluto. We visited Pluto in 2015 thanks to NASA's New Horizons spacecraft. The orbits of Pluto's 5 moons resemble a bullseye, suggesting that they formed together in an ancient collision. New Horizons sped through the target, focusing on Pluto and its moon, Charon. From Pluto's nighttime side, New Horizons observed sunlight streaming through a thin, hazy atmosphere. Pluto's diverse terrain includes towering mountains of water ice and slowly flowing glaciers of frozen nitrogen. Charon, too, has a varied terrain and a vast chasm from which water appears to have erupted and frozen onto the surface. We will learn much more from our brief visit to the Pluto system, but strange as it sounds, we have already learned something from the way it orbits the Sun. If we look at the orbits of Pluto and its many neighbors, we find evidence for a violent rearrangement of the planets.
The discovery of Pluto and its many neighboring Kuiper Belt objects has been a gold mine when it comes to scientific discovery. When we look at our familiar solar system, we are seeing the orbits of the planets, but you may have heard about Pluto and some of its companions being changed to dwarf planets. It turns out there are many of these dwarf planets on the outer edge of our solar system, but the ones we're showing you here are actually the discoveries of a single researcher and his team, Dr. Mike Brown. Now, Dr. Brown has been focused on the outer parts of our solar system and has learned a whole bunch about what we see here, but it's also uncovered some new mysteries. When we look at these distant dwarf planets, we are seeing a class of objects that still hangs out in that Kuiper Belt of our solar system. If we wanted to see it in a greater context, though, we're going to have to change our angle just a little bit. These dwarf planets have names like Eris, Haumea, Makemake, Quaoar, new additions to our solar system. But there's another named object that travels significantly farther from the Sun. This is not a dwarf planet. It's called Sedna. Now, what is Sedna? We're still not really sure. In order to qualify as a dwarf planet, it would have to be massive enough to make itself round, and we're not quite sure if it is. So it travels a much greater distance from the Sun, and that actually means it's part of not only the Kuiper Belt for part of its orbit, but also the Oort cloud, an outer body of comets that surrounds our solar system. By traveling between the two populations, it kind of keeps itself ambiguous. We're not exactly sure how to classify it. But it's also not alone. We have found out that amongst Sedna and its tilted orbit, there are many other objects filling in this part of our solar system. These objects, though, as you look at their orbits, and many of them don't have names yet, that's how new they are tilted towards one side of our solar system. And that seems a little bizarre. How come there are so many on one side, but not the other? Well, this led Mike Brown and his team to an interesting conclusion. It's possible that all of these objects just happened to be on the same side of our solar system, but that's about a 1 in 70,000 chance. A more likely situation would be that they were pushed towards one side by a body or bodies on the other side. So they began plugging into their computers guesses about the mass, the potential size of an object that could have steered these things. And the most likely scenario, after many, many calculations, is another planet. Now, what would this planet look like? It would have a huge orbit biased towards the other side of the solar system. Now, a huge orbit like this has not been found in our solar system before. It would travel between 200 Earth distances of the Sun at its very closest approach, what we call perihelion, and between 1,000 times farther at its farthest. 100 times farther, 2,000 AU. So when we look at this distribution, it kind of makes sense. It makes the solar system balance out. But what would a planet like this look like? Well, since we don't have telescopic observations of it, no one's quite seen it yet, we're forced to guess. But we have seen Uranus, Neptune, and we've learned about some of these icy bodies at the edge of our inner solar system. And we think this world might be in some ways similar. So when we imagine an ice giant like this, we are forced to draw a couple big guesses. It might have a thin atmosphere. It's probably covered in icy stuff that would be liquid closer in. But an ice giant like this, even though it's new in our solar system, is not completely unheard of. Because one of the most exciting parts about Mike Brown's team's discovery is that these ice giants are probably very common in the universe. In fact, the super Earths we have found in dozens of other solar systems are probably in some ways related to our 9th planet. These gigantic worlds have been found all over. Now, in finding a planet like this, we've seen potentially what might be the very beginnings of a planet like Jupiter. But early on in our solar system's history, it was thrown out into those icy reaches and never completed its formation.
All the places we have visited tell us different parts of the same story. A story that began 4.6 billion years ago with the birth of our solar system. After the sun ignited, most of the material around it had flattened into a disk. We have used computers to simulate what happened inside the disk. Here, a dense swarm of objects collided with one another. Some stuck together to form what astronomers call planetesimals. Pulled together by gravity, some planetesimals formed the planets. Others became asteroids and comets. As the planets grew, they carved out gaps in the dusty disk. If we look at the orbits of the planets and move time at warp speed, so 1 million years pass by every 10 seconds, we can watch how the debris will clear. We've seen how small objects such as Itokawa and Chuo can migrate through the solar system. But even the giant planets shifted orbits in the past, causing gravitational havoc. Many unlucky asteroids and comets and dwarf planets got kicked out of the solar system altogether. A few, including Pluto, settled into orbits that allowed them to coexist safely with the planets. And many tiny objects scattered through the solar system, cratering the surfaces of the inner rocky worlds. We call this burst of chaos the Late Heavy Bombardment. Once things settled down, about 3.8 billion years ago, the orbits of the planets stabilized and a much less cluttered solar system remained. Earth back then looked very different. The constant stream of objects hitting Earth may have brought surprisingly fragile but life-crucial chemicals along with them, including water, nitrogen, and carbon dioxide. That chemical payload may also have included complex organic precursors of life, or perhaps those compounds formed in collisions. Our planet became a laboratory for complex chemistry to develop. Life seems to have begun on Earth as soon as the bombardment ended. In fact, impact craters may have provided places to kickstart the chemistry of life. We can see similar impact evidence on the ancient moon. If we fast forward through time from the end of the late heavy bombardment to the present, we can watch as the moon's cratered surface is covered over by its familiar mare, vast pools of dark lava covering its surface. Occasional infrequent impacts continue to scar the moon's surface. The largest leave behind bright craters and long streaks. We see the moon's history written on its surface. Earth has suffered even more impacts than our sister moon, but has erased the scars that show it. And however violent our history, it could have been worse. The migration of the icy giants and ensuing chaos of the late heavy bombardment likely cleared the solar system of many dangerous objects. Instead of a steady stream of life-altering impacts on Earth, we rarely experience major events. However, small visitors from space arrive all the time. We detect airbursts caused by asteroids. Over more than a decade, we have cataloged hundreds of them peppering the globe. Measured in equivalent tons of TNT, these explosions ranged in size from a few tons to hundreds of thousands. The most powerful of these bursts took place on February 15, 2013, over the Russian city Chelyabinsk. Almost 20 meters in diameter, slightly smaller than Morrison Planetarium, a stony meteor entered our atmosphere at a shallow angle, leaving a trail that stretched more than 100 kilometers. When the main part of the meteor fragmented, it created a burst of light brighter than the sun, and a shock wave that took almost a minute to reach the ground. As the meteor slowed and continued its gentle arc toward Earth's surface, that shock wave shattered windows and damaged buildings in the places highlighted here. Nearly 1,500 people sought medical attention in the next few days, mostly for injuries from shattered glass. We can compare the size of the blast to the area of metropolitan New York City, or the San Francisco Bay Area, or Greater Tokyo. No one saw the Chelyabinsk meteor coming, but these events occur all the time. So, how can we avoid being surprised in the future? We have developed plans to deflect or destroy incoming asteroids, but we need to find them first. To date, we have discovered only a few percent of the near-Earth objects larger than the Chelyabinsk meteor. Our current map of the inner solar system looks crowded enough, but we estimate we will find 100,000 more NEOs. One proposed mission, Sentinel, dedicates a privately funded space telescope to search for NEOs. Scanning in infrared light, it will see asteroids warmed by sunlight. Sentinel should spot 90% of NEOs with diameters greater than 100 meters. On Earth, many telescopes catalog the locations of asteroids and NEOs and we are finding them faster than ever. But the task demands diligence. A project under construction in Chile, the Large Synoptic Survey Telescope, will survey the entire sky every few days. Its frequent observations and extraordinary sensitivity will allow it to detect faint moving objects, including asteroids and NEOs. Once we find these objects, we study them. They tell us about our past, where we came from, why Earth remains a special place for life. When you gaze up at the scarred face of the full moon, you can reflect on the eons of impacts etched on its surface. And when you spot a meteor streaking through the sky, you can recognize a tiny cousin of the objects that influenced life on Earth long ago. In these moments, we look to the past and glimpse the future, recognizing life's deep connection to the universe around us.
Thank you for joining us here for Incoming. As the lights come up, but before